Hello, my curious friends, and welcome to the channel. Wherever you are in the world, whatever the hour on your clock, I'm so glad you're here. Maybe you're winding down for the night, or perhaps this is the sound accompanying your early morning. Maybe you're just seeking a quiet moment in the middle of a busy day. Wherever and whenever you are, take a deep breath, get comfortable, and let your mind relax. Before we drift into tonight's topic, I have a quick but wonderful request. If this is your first time with us, consider subscribing to the channel. It truly helps us grow this quiet community. And if you're already part of our family, a like on this video is a wonderful way to let me know you're enjoying the journey. Most importantly, I'd love to hear from you. Drop a comment down below and tell me just two things: your location and what time it is for you right now. It's always so fascinating to see our community of curious minds spanning the globe in a single moment. Now, for tonight's adventure, we are going on a journey to the very edge of modern science, to a place where the rules of reality as we know them begin to bend and blur. We're going to explore a question that sounds like it's straight out of science fiction, but is actually happening in labs around the world right now. Do quantum computers exist today? We're going to talk about the mind-bending ideas that make them possible, how something can be in two places at once, how particles can be spookily connected across vast distances, and how scientists are trying to harness this quantum weirdness to build a machine of unimaginable power. It's a story of ice-cold temperatures, cosmic puzzles, and a race to build the future. So, if you're ready to let your curiosity drift into the strange and wonderful world of the quantum, then let's begin. Imagine, if you will, a library. Not an ordinary library, but one of almost impossible scale. It contains a book for every single person on Earth, for every thought they've ever had, every story they've ever told. And then, it contains a book for every person who could have existed, for every story that was never written. This library is so vast that if you were to walk its shelves, you would never, in 1,000 lifetimes, see even a fraction of its contents. Now, imagine a reader who doesn't stroll through the aisles one by one, but who, in the blink of an eye, can stand in every corridor, scan every shelf, and read every book simultaneously. This reader doesn't choose one path through the library. They take all paths at once. This, in its essence, is the breathtaking promise of a quantum computer. It's a machine that doesn't think in straight lines, but in a shimmering, probabilistic cloud of every possible answer at the same time. It sounds like pure science fiction, the kind of thing you'd find in a starship's engine room. So, it's a fair question to ask, a question that hangs in the air between the tantalizing theories of physicists and the gritty reality of engineering. Do quantum computers exist today? The answer is a fascinating, nuanced, and absolutely thrilling yes and no. It's a yes that comes with so many asterisks, it looks like a tiny constellation of caveats. To understand that answer, to really wrap our heads around it, we need to embark on a journey. A journey not just into the cold, sterile clean rooms where these machines are built, but into the very heart of reality itself, into the bizarre and counterintuitive rules that govern the universe at its smallest scales. We need to talk about what a quantum computer actually is, how the ones we have today work, and why the dream of a quantum computer in every home, or even in every major research lab, is still a dream facing monumental challenges. This isn't just a story of engineering. It's a story of physics, of materials science, of computer science, and of a global race to tame the quantum world. So, get comfortable. Let's leave our classical, straightforward world behind for a little while and step into the fuzzy, fantastic, and utterly bewildering quantum realm. First, we have to lay the groundwork. What makes a quantum computer so special? Why all the fuss? To understand that, we need to appreciate the workhorse of our modern world, the classical computer. So we've established that our classical computers, these marvels of modern engineering, are fundamentally built on a principle of absolute certainty. A bit is a tiny, unwavering soldier, holding its ground as a definitive 0 or a 1. This binary language is the bedrock of the digital age. But to truly appreciate why this certainty becomes a limitation, we need to dive a little deeper into what it means for a computer to solve a problem. Let's peel back the layers on that idea of the library, because the devil, as they say, is in the details. And in this case, the details are exponentially terrifying. Imagine that library isn't just vast, but that its layout is specifically designed to be as inefficient as possible for our classical librarian. The problem of finding one specific book is bad enough, but now let's consider a problem that's even more complex. We need to find a set of books that, when read together, satisfy a very particular and intricate condition. For instance, imagine we need to find 10 books whose titles, when the first letters are arranged in order, spell out the word butterflies. But there's a catch. We can't just look at the titles. We have to check the books in combination. The first book's title must start with a B, the second with a U, and so on. A classical computer, our speedy but single-minded librarian, would have to start with one possible B book. Then, for that book, check every single U book in the library, and for each of those BU pairs, check every T book, and on and on. The number of possible combinations it would have to check doesn't just grow, it explodes. This is what computer scientists call exponential growth. It's not like adding more rooms to the library. It's like every time you add one more letter to the word you're looking for, the library multiplies in size. For a short word like cat, the number of combinations might be manageable. But for butterflies, with 10 letters, the number of possible paths our librarian would have to walk becomes astronomically large, so large that even if the librarian could check 1 billion combinations per second, it would still take many lifetimes of the universe to check them all. This is the wall that classical computers hit. They are stuck in a sequential nightmare, where each additional variable in a problem multiplies the time required to find a solution. This exponential explosion is precisely what happens in the problem of factoring large numbers, which I mentioned briefly. Let's make that analogy concrete. Imagine the number we want to factor is like a massive multi-story building with a single, giant combination lock on the front door. The combination is the two prime numbers that, when multiplied, give you the address of the building. A classical computer's approach is to try every single possible combination. It starts at 0000, then 0001, and so on. Because the numbers are so immense, often hundreds of digits long, the number of possible combinations is not just huge, it's exponentially huge. It's like the combination lock has not 3 dials with 10 numbers each, but hundreds of dials, each with 10 numbers. The time required to try all combinations becomes so astronomically long that for all practical purposes, the lock is unbreakable. Our entire system of online security is built on the faith that no classical computer will ever have enough time to spin those dials through all the possibilities. But now, let's spend some more time on the second example, because it's perhaps even more profound and gets us closer to the heart of why quantum computing is so revolutionary. Simulating molecules. This isn't just about breaking codes, it's about understanding and creating the very fabric of our world. Think about a simple molecule, like a caffeine molecule, that gives your morning coffee its kick. This molecule is a tiny, intricate dance of atoms: carbon, hydrogen, nitrogen, oxygen, all held together by a web of electrons. Now, in the old classical picture of the atom that many of us learned in school, electrons are like little planets orbiting a sun-like nucleus. This model is neat and tidy, but it's also completely wrong for describing how things actually behave at the molecular level. In reality, electrons don't live on neat planetary orbits. Instead, they exist as probability clouds, often called orbitals. An electron isn't here or there. It has a probability of being here and a probability of being there. And it's actually in a sort of smeared out existence across all those probable locations at once, until something forces it to pick a spot. This is superposition at the subatomic level. It's the quantum world's inherent fuzziness. When two atoms bond to form a molecule, their electron probability clouds merge and interact in incredibly complex ways. The exact shape and energy of this merged cloud determine everything about the molecule: how stable it is, how it reacts with other molecules, what color it is, how it absorbs light. To simulate a molecule on a classical computer, you have to calculate the behavior of every single electron in relation to every single atomic nucleus and every other electron. But because each electron is in a probabilistic superposition, the classical computer has to painstakingly calculate the probability for every possible configuration of every electron. It's like trying to write down the recipe for a cake by describing the precise location and velocity of every single atom of flour, sugar, and egg. It's possible in theory, but the calculations required are so monstrously complex that even simulating a relatively simple molecule, like caffeine, with perfect accuracy, pushes the limits of our most powerful supercomputers. And that's just for one static molecule. To design a new drug, you need to simulate not just the drug molecule, but also the enormous protein molecule in your body that it's supposed to interact with. You need to simulate how they dance around each other, how they fit together like a key in a lock, and how that interaction alters the protein's function. This dance is a dynamic, quantum mechanical ballet. With classical computers, scientists are forced to use rough approximations and simplifications. They might treat atoms as little balls and springs, ignoring the quantum behavior of the electrons altogether, because including it is just too computationally expensive. It's like trying to predict the weather by only considering the temperature and ignoring wind, humidity, and pressure. You might get a vaguely right answer sometimes, but you'll miss all the nuances, the storms, the subtle shifts. This is why drug discovery is such a slow, expensive, and trial and error heavy process. It can take over a decade and billions of dollars to bring a single new drug to market, in large part because we're trying to simulate a quantum reality with classical tools that are fundamentally ill-suited for the task. This is the fuzzy cloud of probabilities I mentioned. It's not just an academic curiosity. It's the central reality of chemistry, materials science, and biology. When we try to paint this quantum reality using only the black and white paint of classical bits, we are, as the saying goes, trying to fit a square peg into a round hole. The approximation will always be crude. We might get the general shape right, but we'll never capture the true, vibrant, and often surprising colors of nature's masterpiece. This limitation extends far beyond drug discovery. Think about designing a new material. Perhaps we want to create a super efficient catalyst that can break down carbon dioxide from the atmosphere, or a new high-temperature superconductor that can transmit electricity without any loss, revolutionizing our power grid. These properties are all determined by the quantum mechanical interactions of electrons within the material. We have amazing theoretical models for how these interactions work, but without the ability to simulate them accurately, we're essentially guessing. We synthesize thousands of candidate materials in the lab and test them, a slow and expensive process. A quantum computer, which naturally speaks the language of electrons and probability clouds, could in theory simulate these materials from first principles, allowing us to design them virtually on a screen before we ever step foot in a laboratory. It would be like moving from alchemy to precise chemical engineering. So, the fuss about quantum computers is not just that they might be faster, it's that they represent a fundamentally different way of processing information, one that is aligned with the underlying rules of our universe. A classical computer is like a brilliant logician who thinks in strict, sequential, yes-no statements. A quantum computer is like a visionary artist who can perceive all the shades of maybe, all the possibilities at once, and intuitively see the pattern that emerges from the chaos. The classical computer is perfect for the world we've built, the world of spreadsheets, word processors, and video streams. But to understand and manipulate the natural world, the world of molecules, materials, and perhaps even the foundations of intelligence itself, we need a tool that operates on nature's own terms. This is the grand promise. It's the reason why governments, tech giants, and startups are investing billions of dollars in this technology. They are betting that we can learn to harness the bizarre laws of quantum mechanics not just as a scientific curiosity, but as a practical engineering material. We are trying to build a ladder out of the flat, two-dimensional landscape of classical computation and into the rich, multidimensional, and probabilistic world of quantum reality. It's a staggering ambition. And it all starts with learning to build and control a single stable qubit, that fragile speck of possibility that can be both a 0 and a 1 at the same time. The journey from understanding why we need it to actually building it is a story of overcoming some of the most daunting engineering challenges humanity has ever faced. This is where the quantum bit, or qubit, comes in. The qubit is the fundamental unit of quantum information, and it is where our journey into the weirdness begins. If a classical bit is a light switch, a qubit is, well, it's something much stranger. Imagine a sphere. A classical bit can only be at the very north pole, which we'll call 0, or the very south pole, which we'll call 1. A qubit, however, can be anywhere on the surface of that sphere. This is thanks to a quantum property called superposition. Superposition is the ability of a quantum system to be in multiple states at the same time. So, a qubit isn't just a 0 or a 1, it can be a blend of both, a probabilistic mixture represented by a point on that sphere, often called the Bloch sphere. The exact position on the sphere describes the probability that when we measure the qubit, it will collapse to a 0 or a 1. It's like spinning a coin. While it's spinning, it's neither heads nor tails, but in a superposition of both. It's only when it lands, when we measure it, that it becomes definitively heads or tails. This is the first secret power of quantum computing. A single qubit can hold a spectrum of information, while a classical bit holds only one definite piece. But one qubit on its own isn't very useful. The real magic happens when you have multiple qubits and they become entangled. Entanglement is perhaps the most famous and most spooky concept in quantum physics. It's a connection between qubits that is so profound that they lose their individual identities and become part of a single, unified quantum system. When two qubits are entangled, the state of one is instantly correlated with the state of the other, no matter how far apart they are. If you measure one and find it to be 0, you know with absolute certainty that its entangled partner is 1, or vice versa, depending on the type of entanglement. It's as if you had two coins spinning in perfect correlation. If you catch one and see its heads, you instantly know the other is tails, even if it's on the other side of the galaxy. Einstein called this spooky action at a distance because it seems to violate the speed of light, but it's been proven experimentally time and time again. This is the heart of the magic trick. And like all the best magic tricks, it relies on a subtle understanding of the audience's perception, in this case, the perception of reality itself. We've set the stage with our qubits, these amazing little objects that can be in a blend of states. We've introduced the spooky connection of entanglement, linking their fates together. Now we throw the switch and watch the whole system light up with parallel possibilities. But the critical thing to remember, the part that separates the dream from the deliverable, is that this magnificent parallel computation is happening in the shadows. It's a performance behind a curtain. When we finally yank the curtain open to see the result, the performance is over and we're left with a single, static outcome. The trick isn't to see the whole performance, it's to rig the show so that when the curtain goes up, the actor we want to see is standing center stage, bowing. Let's make this concrete. Let's go back to our two qubits. Imagine each one is a special kind of light bulb, but instead of being simply on or off, it can be in a state of being both on and off, with a certain probability for each. Now, if these two light bulbs are independent, not entangled, then the system of both is just a combination of their individual states. It's a bit murky, but not truly parallel. But when we entangle them, we create a single, unified quantum system. It's no longer two separate light bulbs, it's one quantum light system with 4 possible classical outcomes. And because of superposition, this entire system exists in a blended state of all 4 possibilities. Both off, 0, 0, first off, second on, 0, 1, first on, second off, 10, and both on, 11. It's not cycling through these states quickly. It is all of them simultaneously. The information of all 4 states is present in the quantum description of this tiny 2-qubit system. Now imagine each of those 4 states, 0, 0, C1, 10, 11, represents a single unique path through a very simple maze. A classical computer would have to try each path, one after the other. It would walk down the U0 path, hit a dead end, backtrack, walk down the U1 path, and so on. Our 2-qubit system, however, exists at the entrance of all 4 paths at the same time. It's as if it has 4 ghostly versions of itself, each exploring one route simultaneously. This is the source of the quantum parallelism you hear about. Scale this up. With 3 qubits, you have 8 paths, 0, 1, 0, 10, 11, 100, 101, 110, 111. With 50 qubits, you have over a quadrillion paths. That's a 1 with 15 zeros after it. To put that number in perspective, if you could count one number per second, it would take you over 30 million years to count to a quadrillion. A quantum computer with 50 perfectly functioning qubits could, in principle, Explore all those quadrillion paths in the time it takes to execute a single sequence of quantum operations. With 300 qubits, the number of paths surpasses the number of atoms in the observable universe. This is not just a big number, it's an incomprehensibly vast number. The potential is, quite literally, universe-sized. This is why the quantum librarian analogy is so powerful. The classical librarian, for all their speed, is stuck in a single aisle reading one book at a time. The quantum librarian is in every aisle, reading every book at once. But here comes the great cosmic catch. Let's say you ask the quantum librarian a question. Find me the book that contains the secret to room temperature superconductivity. The librarian, being quantum, instantly accesses every book. But when you turn to the librarian and say, "Okay, tell me the answer," something profound happens. The librarian can only tell you about one book, just one. The act of asking the question, of demanding an answer, forces the entire superposition to collapse into a single, random result. You might get the correct book. But with a quadrillion books to choose from, the odds are overwhelmingly high that you'll just get a random novel or a cookbook. The librarian experienced all the books, but can only report on one. So, if all we did was set up a superposition and then immediately measure it, a quantum computer would be worse than useless. It would be a random number generator. This is the central, beautiful puzzle of quantum computing. The power is in the parallel exploration, but the answer is singular. So how do we extract a useful, specific answer from this ocean of possibility? We don't just let the quantum system explore all paths. We must cleverly program it so that the paths we don't want interfere with each other destructively, canceling each other out, while the paths we do want interfere constructively, amplifying each other. We have to choreograph the quantum waves of probability. Think of it like this. Imagine you're in a large, empty concert hall with perfect acoustics. You have 2 speakers set up, and you play a pure, single musical note through both. Sound travels in waves. Now, if you stand in a spot where the crest of a wave from the left speaker arrives at exactly the same time as the crest of a wave from the right speaker, they will add together. The sound will be louder. This is constructive interference. But if you move to a spot where the crest of a wave from the left speaker arrives at the same time as the trough of a wave from the right speaker, they will cancel each other out. The sound will be silent or very quiet. This is destructive interference. In a quantum computer, each possible computational path is like a sound wave. Each path has a so-called probability amplitude, which you can think of as the wave's height and direction, its phase. When we finally measure the system, we don't see the individual waves. We see the final combined effect of all waves added together. The goal of a quantum algorithm is to arrange things so that for all the wrong answers, the probability waves are like crests meeting troughs. They cancel each other out. For the one correct answer, the waves are all crests meeting crests. They combine to create a massive wave, a tsunami of probability. So, when we finally make the measurement, the system doesn't just randomly pick any state from the superposition. It picks a state with a probability determined by the square of its combined wave's amplitude. If we've done our quantum choreography correctly, the probability for the correct answer will be close to 100%, and the probability for all the wrong answers will be close to 0%. The wrong answers vanish into silence, and the right answer rings out like a clear, loud bell. This choreography is accomplished using quantum logic gates. These are the basic building blocks of a quantum circuit. If classical logic gates, AND, or not, are simple tools for manipulating definite bits. Quantum gates are sophisticated instruments for sculpting probability waves. They gently nudge the qubits, rotating their state on that block sphere we imagined earlier, and creating and manipulating entanglement between them. Some key quantum gates are like the basic notes in this symphony. A simple gate might just flip a qubit from a 0 to a 1, like a classical NOT gate. But a quantum version can do much more. It can put a qubit that is definitely 0 into a perfect superposition of 0 and 1. Another crucial gate, called the Hadamard gate, is the superposition creator. It takes a qubit that is in a definite state, say 0, and puts it into a state of equal superposition, a 50-50 chance of being 0 or 1 when measured. This is how we create our parallel explorers at the start of a computation. Then there are gates that create entanglement, like the C-NOT, controlled NOT gate. This gate takes 2 qubits. It leaves the first one alone, but it flips the state of the second qubit only if the first qubit is 1. When applied to qubits in superposition, this operation creates the deep, correlated connection that is entanglement. The fates of the 2 qubits become intertwined. A quantum algorithm, then, is a precisely timed sequence of these gates, a dance of rotations, flips, and entanglements, applied to an initial set of qubits. Each gate slightly alters the complex pattern of probability waves spreading through the vast landscape of possible answers. The algorithm is designed so that after the final gate is applied, the waves for the incorrect answers have all but canceled each other out, and the wave for the correct answer stands tall and dominant. This is why writing software for a quantum computer is so different and so difficult. You're not writing a list of instructions. You're composing a piece of music for an improbability wave orchestra. You have to think about the relative phases and amplitudes of different computational paths. It's a deeply counterintuitive way of programming, which is why the discovery of a new efficient quantum algorithm is a major event. So, to recap this crucial point, the immense power of a quantum computer does not come from it checking a quadrillion possibilities and then handing you a list of all the correct ones. That would be impossible, as the measurement collapses the superposition. The power comes from its ability to use interference, a fundamental wave phenomenon, to make the wrong answers vanish and the right answer shine through. It's a subtle but profound distinction. We are not using the quantum computer as a massive parallel processor whose results we simply read out. We are using it as a sophisticated waveguide shaped by quantum gates to force the universe itself to reveal the answer to us by amplifying the signal of truth and silencing the noise of falsehood. It's a dialogue with nature, conducted in nature's native tongue, and learning to speak that language fluently without the conversation being disrupted by the outside world is the great challenge that lies ahead. So, with all this talk of theoretical magic tricks and choreographing probability waves, you might be wondering, is this all just a beautiful idea scribbled on blackboards, or have we actually managed to build something? Well, let me tell you, the journey from theory to reality is well underway. It's a bit like the early days of flight. For centuries, people dreamed of soaring like birds, drawing designs for flying machines that were elegant in theory, but crumpled on takeoff. Then, finally, the Wright brothers got a rickety contraption to hop a few feet off the ground for a handful of seconds. It wasn't a transatlantic jet, but it was undeniable proof that flight was possible. Today's quantum computers are our Wright Flyer moments. They are real, they are tangible, and they are doing things that no classical machine can do, even if those things are, for now, more about proving a point than delivering a product. Yes, quantum computers exist today. That's a fact you can experience for yourself. If you have an internet connection, you can go to the website of a company like IBM, create an account, and within minutes, you're given access to their quantum computing platform. You can drag and drop quantum gates onto a virtual circuit, stringing together a sequence of operations for a handful of qubits. Then you can hit run, and your circuit isn't just simulated on a classical computer. It's sent to a data center where a real physical quantum processor, housed in a gigantic dilution refrigerator colder than the void between stars, executes your code. You're programming a machine that manipulates the quantum states of actual subatomic particles. It's an utterly mind-boggling concept that has become remarkably mundane for researchers in the field. This isn't science fiction. It's a service you can use right now. But, and this is a very important but, if you expect this quantum computer to instantly solve all your problems or crack the encryption on your email, you're going to be deeply disappointed. The circuits you can run are small. The results you get are often noisy, meaning they're sprinkled with errors. It's like having a telephone line to the moon. The fact that you can call at all is a miracle of engineering, but the connection is full of static, and you can only have a very short, simple conversation. This is the current state of the art. This is what experts mean when they talk about the era of noisy, intermediate-scale quantum devices, or NISQ for short. It's a term that packs a lot of meaning into 3 words, and understanding it is key to seeing the quantum landscape clearly, without the hype or the undue pessimism. Let's start by unpacking the intermediate scale part. This refers to the number of qubits we can currently control and link together. We're not talking about the thousands or millions of error-corrected logical qubits needed to run an algorithm like Shor's to break encryption or simulate a complex molecule with perfect accuracy. Not yet. We're in the realm of tens to a few hundred physical qubits. To appreciate what this means, let's go back to our library analogy. A classical supercomputer is like a team of 1 billion librarians, each incredibly fast, but each still checking one book at a time. A quantum computer with 50 perfect qubits would be like a single librarian who can simultaneously be in a quadrillion aisles. But our current quantum computers are like having a librarian who can be in 50 or 100 aisles at once. That's still an astronomical number of paths, far beyond what any classical computer could handle for a problem designed to exploit that parallelism. But it's a far cry from the infinite library we ultimately need to explore. Companies are in a steady race to increase this number. IBM has been steadily releasing processors with increasing qubit counts, with names like Falcon, Hummingbird, and Eagle, the latter boasting a 127 qubits. Google's Sycamore processor, the star of a major milestone, had 53 qubits. Companies like Rigetti Computing and IonQ are also building processors with tens of qubits. Now, you might think, well, 127 sounds like a lot. My first computer had a processor that was 8-bit, and look how far we came. But with quantum computers, it's not a linear progression. Adding more qubits isn't just about increasing raw power. It's about exponentially increasing the complexity of control and the severity of the errors. Each new qubit added to the processor isn't just another worker. It's another incredibly temperamental artist that has to be perfectly in sync with the entire orchestra, and who is prone to having a coughing fit in the middle of the symphony. The engineering challenge of keeping even 100 qubits coherent and interacting reliably is staggering. This brings us to the landmark event that really put the intermediate scale on the map: Google's 2019 announcement of quantum supremacy. Now that's a term that sounds like it's straight out of a superhero movie, and it certainly grabbed headlines. What did it actually mean? The Google AI quantum team, using their 53-qubit Sycamore processor, performed a very specific task. The task itself was somewhat arcane. It was essentially to verify that a randomly generated quantum circuit produced a certain output distribution. In simpler terms, they asked their quantum computer to create a uniquely complex, random pattern of probability, a kind of quantum fingerprint. Then, they challenged the world's most powerful classical supercomputer, Summit at Oak Ridge National Laboratory, to simulate what the quantum computer had done and predict that pattern. The quantum computer did its job in about 200 seconds. The researchers estimated that for Summit to simulate this and get the same result, it would take approximately 10,000 years. The difference in time was so vast that it was declared a demonstration of supremacy, a point where a quantum computer solves a problem that is practically impossible for a classical computer to solve in any reasonable time frame. It was a historical moment, a proof of concept that echoed around the world. It was the quantum equivalent of the Wright Flyer's first flight, a short, wobbly hop that proved the principle of aerodynamics could be harnessed. But it's crucial to understand what quantum supremacy was not. It was not a demonstration of a useful computation. The problem it solved had no practical application. It was chosen precisely because it was a natural fit for a quantum computer and a nightmare for a classical one. It was a benchmark, a test of raw processing power in a very narrow domain. It's like if you invented a new type of engine that could solve an incredibly complex physics puzzle about tire friction in milliseconds, but couldn't yet power a car to the grocery store. The puzzle doesn't help you with your shopping, but it proves your engine has unique capabilities. Similarly, Sycamore's achievement didn't mean it could break codes or design drugs. It meant that the fundamental quantum advantage, the ability to leverage superposition and entanglement to outperform classical machines, was no longer just a theory. It was a reality in the lab. Since then, the race has continued. Other groups, particularly in China, have claimed similar or even more advanced demonstrations. For instance, a team from the University of Science and Technology of China, USTC, later reported a quantum supremacy experiment using a different type of quantum processor based on photons that they said could solve a similar sampling problem even faster. The field is vibrant and competitive, with national pride and significant commercial investment at stake. Each announcement pushes the boundary of what's possible, incrementally increasing the qubit count and improving the fidelity of the operations. However, living in the NISQ era means that these intermediate-scale machines are only half the story. The more problematic part of the NISQ acronym is noisy. Noise is the enemy of quantum computation. Remember how delicate the state of a qubit is? It's that spinning coin balanced on its edge, exquisitely sensitive to the slightest disturbance. In the real world, qubits are not isolated ideal systems. They are physical objects, perhaps individual atoms or tiny superconducting circuits or photons, and they exist in an environment. Any interaction with that environment, whether it's a stray vibration, a fluctuating magnetic field, or even a cosmic ray, can cause the qubit to lose its precious quantum state. This loss of quantum coherence is called decoherence. It's the process by which the spinning coin gets bumped and falls over, becoming a boring classical heads or tails before we want it to. In a quantum computer, decoherence is the source of errors. A calculation that requires 1,000,000 quantum logic gates is useless if your qubits decohere after only 100 gates. It's like trying to build a house of cards in a wind tunnel. This fragility is the single greatest challenge in building a practical quantum computer. The entire engineering effort revolves around protecting the qubits from the world for long enough to do meaningful computation. This leads us directly into the heart of the current challenges. To build a general-use quantum computer, a machine that can run Shor's algorithm to break RSA encryption or simulate a complex molecule for drug discovery, we need to overcome a series of Herculean obstacles. Let's walk through them one by one in minute detail. So we've arrived at one of the most practical and yet still utterly fascinating parts of our story: the actual physical stuff these machines are made of. If a qubit is the idea, a unit of quantum information, what does it look like in the real world? How do you actually build a thing that can be both a 0 and a 1 at the same time? It turns out there isn't just one answer. It's a bit like asking in 1900, what does a flying machine look like? Some inventors were building gliders with wings. Others were experimenting with helicopters, and a few were even thinking about rockets. The fundamental principle, generating lift, was understood, but the best way to achieve it was a wide-open question. The quest for the perfect qubit is in a similar, gloriously chaotic phase. Different teams are betting on different designs, each with its own brilliant advantages and seemingly deal-breaking drawbacks. Let's take a closer look at the two leading contenders, the workhorses of the current quantum race. First up, the approach you might have heard the most about: superconducting qubits. Used by giants like Google and IBM, these are the quintessential high-tech marvels. Imagine a computer chip, like the one in your phone, but instead of being designed to process billions of bits, it's designed to host a few dozen or 100 qubits. The qubits themselves are microscopic circuits etched onto the surface of the chip. They aren't simple wires. They are often laid out as tiny, squiggly loops or other shapes, and they include a crucial component called a Josephson junction. This junction is essentially a very thin barrier that electrons can cross through a quantum mechanical effect called tunneling. It's this component that gives the circuit its quantum personality. Now here's the first wild part. To make these circuits behave as qubits, we have to change their entire reality. At room temperature, they're just normal boring metal circuits. But when we cool them down, and I mean really cool them down, to a temperature within a few thousandths of a degree above absolute zero, which is the coldest temperature possible in the universe, something magical happens. The materials, often a combination of niobium and aluminum, become superconductors. This means all electrical resistance vanishes. Electrons can flow forever without losing any energy, like a perfectly frictionless slide. In this bizarre, ultra-cold state, the entire circuit stops behaving like a normal object and starts obeying the weird rules of quantum mechanics. It acts like an artificial atom. You can think of it like this. A real atom has discrete energy levels. An electron can be in a low energy ground state, which we could call our zero, or it can be excited to a higher energy level, which we could call our 1. Our superconducting circuit, this tiny loop of wire, does the same thing. Its quantum state is defined by the collective motion of billions of electrons flowing around the loop. This collective motion can have different energy levels, and we can define the lowest level as 0 and the next one up as 1. We can flip the qubit from 0 to 1 by sending a precisely tuned microwave pulse to the circuit, much like hitting a tuning fork to make it vibrate. We can also entangle two qubits by sending microwave pulses that make their fates interdependent. The huge advantage of this approach is scalability. We have decades of experience in the semiconductor industry etching incredibly complex patterns onto silicon chips. We know how to make things small and pack them together. The hope is that we can leverage this trillion-dollar manufacturing knowledge to eventually etch thousands, even millions, of these superconducting circuits onto a single chip. It's a path that looks familiar, and that's a comfort to engineers and investors. But the disadvantages are, as you might expect, monumental. The first is the elephant in the room, or rather, the gigantic refrigerator in the lab. These dilution refrigerators are engineering wonders in themselves, multi-million-dollar systems that are like a Russian nesting doll of cooling stages. They use rare isotopes of helium to achieve temperatures colder than the dark void between galaxies. They are expensive, they consume a lot of power, and they are notoriously finicky. Your quantum processor is sitting in a golden can at the very bottom of this complex stack, in the quietest, coldest place we can create on Earth. The second major disadvantage is the qubits themselves. While tiny to our eyes, these circuits are still enormous from the perspective of an atom. They are made of billions of atoms. This large size makes them like giant sensitive antennae, constantly picking up static from the environment. Any tiny fluctuation in the magnetic field, any minuscule vibration, any stray photon of heat can jar the qubit out of its delicate superposition. It's like trying to balance a pencil on its tip on a table that's being gently tapped by 1,000 tiny hammers. This is the source of the dreaded decoherence. In current systems, superconducting qubits can only maintain their quantum state for mere microseconds, maybe a few hundred microseconds at best, before the noise of the world crashes the party. This short coherence time is the stopwatch that limits how long a calculation can run. Now, let's travel to a different lab, where a different philosophy is at work. Here, the approach is not to build an artificial atom, but to use a real one. This is the world of trapped ion qubits, championed by companies like IonQ and Honeywell. The qubit here is a single individual atom, often a rare earth element like ytterbium or an alkaline earth metal like barium. But there's a catch. To control it, they first strip away one of its electrons, turning it into an ion, an atom with a positive electric charge. This charge is the key to the whole trap. The ion is held perfectly still, suspended in a perfect vacuum, not by any physical container, but by carefully shaped electromagnetic fields. Imagine you're trying to levitate a peanut using a dozen precisely aimed hairdryers. It sounds impossible, but that's the basic idea, executed with incredible precision using metal electrodes that create an ion trap. The ion hovers in the center of a small chamber, isolated from the world. Then, the real magic begins. Scientists use lasers to cool the ion down to a virtual standstill, removing any vestige of heat-induced jiggling. Once it's cold and calm, other lasers, tuned to exquisitely specific frequencies, are used to manipulate its quantum state. The 0 and 1 states are often represented by two different energy levels of the ion's outermost electron. A carefully aimed laser pulse can nudge the electron from one level to the other, performing a quantum gate. The advantages of this method are profound. First, the qubits are perfect. Every ytterbium ion is identical to every other ytterbium ion, provided by nature itself. There are no manufacturing defects. Second, because the ion is suspended in an ultra-high vacuum, it is incredibly well isolated from the noisy environment. there's nothing around to bump into it. This means trapped ion qubits can have remarkably long coherence times, seconds, minutes, even hours. Compared to the microsecond coherence of superconducting qubits, this is an eternity. It's the difference between trying to have a conversation in a quiet library versus in the middle of a rock concert. But of course, there are trade-offs. The major challenge is speed and scalability. The laser manipulations are precise, but they are relatively slow. Entangling two ions can take much longer than entangling two superconducting qubits with a microwave pulse. Furthermore, as you try to build a larger quantum computer with more qubits, you face the scalability problem. You need to trap not just one or two ions, but dozens or hundreds, and you need to be able to address each one individually with a laser without affecting its neighbors. Imagine our dozen hairdryers trying to levitate and individually control 100 peanuts all at once. The complexity of the laser systems and the trap design becomes mind-boggling. While superconducting qubits are fixed in place on a chip, trapped ions need to be shuttled around within the trap to interact, adding another layer of complexity. And the race doesn't stop there. On the horizons of research are even more exotic designs. Topological qubits are a dream technology. The idea is to encode the quantum information not in a single particle, but in the overall shape or braiding of paths that certain quasi-particles take. The beauty of this is that the information would be inherently protected from local noise. Much like the meaning of a knot isn't destroyed if you jiggle the rope a little. It's a profoundly clever idea. But the particles needed to make it work, called Majorana fermions, are still in the early stages of being conclusively observed and controlled. Then there are photonic qubits, which use particles of light. They're fantastic for quantum communication because light travels so well, but getting two photons to interact strongly enough to perform a quantum gate is very difficult. And finally, there are silicon spin qubits, which try to embed qubits into standard silicon chips using the spin of an electron or a nucleus as the 0 and 1. This approach hopes to piggyback on the entire global infrastructure of the computer chip industry. So, you see, the field is a vibrant ecosystem of different ideas. It's not yet clear which design will win out. Perhaps like in aviation, different designs will be used for different purposes. Maybe superconducting qubits will power the massive centralized quantum data centers, while trapped ions will be used for specialized, high-precision calculations. The journey to build a practical quantum computer is as much a story of materials science and electrical engineering as it is of physics. It's a race to find the best possible vessel to carry our fragile quantum information on its journey through the waves of probability. And keeping that information safe on that journey is the next great challenge, the problem of error correction. The second monumental challenge, intertwined with the first, is error correction. In a classical computer, error correction is straightforward. Information is redundant. You can store a bit of information across 3 bits. 0 becomes 0, 0, 0. If one of them flips due to a cosmic ray, say 0, 0 and becomes 0, 10, a simple majority vote corrects it back to 0, 0, 0. You can't do this with a qubit because of the no-cloning theorem, a fundamental rule of quantum mechanics, which states that you cannot create an identical copy of an unknown quantum state. You can't just make a backup of your spinning coin. Furthermore, measuring the qubit to check for an error would collapse its superposition, destroying the very computation you're trying to protect. So, quantum error correction, QEC, is infinitely more subtle and complex. The leading idea is to use multiple physical qubits to create one, more stable, logical qubit. Instead of storing the quantum information in a single, fragile physical qubit, it's spread out across an entangled array of many. The most famous scheme is the surface code, where physical qubits are arranged in a grid. By making clever, indirect measurements on groups of these qubits, measurements that don't reveal the actual quantum information, but only tell you about the pattern of errors, you can detect if an error has occurred and what kind, without collapsing the main computation. It's like having a network of canaries in a coal mine. The canaries dying tells you there's poison gas, but it doesn't tell you what the miners are saying to each other. You protect the message by monitoring the environment around it. The catch? It's extravagantly expensive. Current estimates suggest you might need anywhere from 1,000 to 10,000 physical qubits to create a single, stable, error-corrected logical qubit. And for a useful, general-purpose quantum computer, you would likely need thousands of these logical qubits. This means we are talking about building a machine with millions of physical qubits. We currently have processors with a few hundred at best. This is the scalability problem in its starkest form. We not only need to build qubits, we need to build them with incredibly high quality, long coherence times, and in mind-boggling numbers, all while keeping them isolated and controllable. It's a manufacturing challenge that dwarfs anything the classical computer industry has ever faced. The third challenge is control. How do you talk to these qubits? How do you perform the precise quantum gate operations that constitute an algorithm? For superconducting qubits, this involves a labyrinth of wires, microwave wires, DC wires, all running from room temperature down into the super-cold heart of the dilution refrigerator. Each qubit needs its own control lines. As you add more qubits, this wiring problem becomes insane. You can't have 1,000,000 wires going into a fridge. There simply isn't room, and the heat load would be impossible to manage. This is a major bottleneck for scaling up superconducting architectures. Solutions being explored include integrating control electronics closer to the qubits, inside the fridge itself, or using multiplexing techniques to reduce the number of wires. For trapped ions, the control system is a laser rainbow, an array of lasers so precise they can address individual ions in a chain. Scaling this to thousands of ions would require a level of optical control that is currently science fiction. The fourth challenge is the software and algorithms. Even if we had a perfect, large-scale, error-corrected quantum computer tomorrow, we wouldn't immediately know what to do with it. We need to develop the algorithms that can leverage its unique strengths. This is an active area of research. Shor's algorithm for factoring and Grover's algorithm for database search are famous early examples, but the field is exploring quantum machine learning, quantum optimization for logistics and finance, and of course, quantum chemistry simulation. Writing code for a quantum computer is nothing like classical programming. You are essentially designing a quantum circuit, a sequence of gates that manipulate the quantum state, and you have to think in terms of probabilities and interference. The development tools, languages like Qiskit, Cirq, and Qwant, and simulators are all in their infancy. Furthermore, for the NISQ era, we need algorithms that are shallow. They can't have too many steps, so they can finish before the qubits decohere. Finding useful, real-world problems that fit this description is a huge challenge in itself. The fifth challenge is one that is often overlooked but is absolutely critical: the classical interface. A quantum computer will not be a standalone device. It will be an accelerator, much like a GPU is today, working in tandem with a powerful classical computer. The classical computer will be responsible for preparing the problem, feeding the quantum circuit to the quantum processor, and then processing the results that come out, which are just statistical samples. For complex problems, this will require a tremendous amount of classical computing power and a very high bandwidth connection between the classical and quantum systems. The output of a quantum computation is not a single clean answer like 42. It's a histogram. You run the same quantum circuit thousands of times, and each time you get a potentially different bit string result due to the probabilistic nature of measurement. The correct answer is the one that appears with the highest probability. This requires a massive amount of classical post-processing. Finally, there is the challenge of integration and cost. A state-of-the-art quantum computer today is not a sleek little box. It's a Rube Goldberg-esque collection of extreme technologies. The dilution refrigerator alone is a multi-million-dollar device the size of a telephone booth, requiring specialized infrastructure and a constant supply of expensive liquid helium. The control electronics racks fill an entire room. The whole system consumes vast amounts of power. Making this technology accessible, reliable, and affordable is a journey that will take decades. The path forward is likely not a single breakthrough, but a long, slow slog of incremental improvements in qubit coherence times, gate fidelities, control systems, and error correction schemes. So where does this leave us? Do quantum computers exist today? Absolutely. They are real physical machines that are teaching us an immense amount about the quantum world and how to control it. Have they achieved their ultimate potential? Not even close. We are in the analog of the 1940s for classical computing. We have our ENIACs, huge, fragile, room-filling machines that can perform specific calculations faster than any human, but are not yet general-purpose tools that will change society. The challenges are profound, spanning physics, engineering, and computer science. But the progress is relentless. Every year, qubit counts go up, coherence times get longer, gate fidelities improve, and new algorithms are discovered. The global investment from governments and private companies is staggering. The promise is too great to ignore. A fully realized quantum computer could help us design new materials to solve the energy crisis, discover new life-saving drugs by simulating biology at an atomic level, and unravel the deepest mysteries of the universe itself. The journey from the noisy, intermediate-scale devices of today to the fault-tolerant quantum computers of tomorrow is one of the great scientific and technological adventures of our time. We are not just building a new computer, we are learning to speak the native language of the universe. And that is a story worth following, one qubit at a time. Good night, and have a deep, calm sleep.